Early December 1943, Kummersdorf Proving Ground, Brandenburg, Germany. The morning temperature had dropped to -18 degrees Celsius overnight. Frost covered every surface of the captured American tank, its hull still bearing armor thickness measurements stenciled across the metal by German test engineers. Personnel from the Army Weapons Office gathered in the pre-dawn darkness, their breath visible in the frigid air, clipboards already in hand despite the cold making their fingers ache. Before them sat the M4A1 Sherman designated for cold weather engine testing. The tank bore the name War Daddy 2, painted on its hull during its previous service with Company G of the 1st Armoured Regiment, 1st Armoured Division. Captured at Sidi Bou Zid in Tunisia 9 months earlier, this Sherman had already undergone extensive automotive testing that summer. But now, with German forces deep into their third winter on the Eastern Front, a new question demanded answers. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Could American tanks function in the brutal cold that had paralyzed so much German equipment? German tank crews knew winter's arithmetic with bitter precision. At -20 degrees Celsius, their Maybach engines required hours of preparation before starting. Coolant and lubricating oil had to be drained the previous evening, heated overnight using precious fuel or open fires, then carefully poured back into the engine at first light. Even then, hand-cranked inertia starters supplemented electric motors that could barely turn over cold engines. Battery efficiency plummeted in freezing temperatures, and many mornings saw entire tank companies immobilized while crews labored to coax life into frozen machinery. The test protocol for this December morning was straightforward but demanding. The Sherman would sit exposed to ambient temperature overnight with no preparation, no preheating, no special winterization procedures. At 0600 hours, test engineers would attempt to start the Continental R975 Radial engine using only the tank's standard electric starter motor, exactly as an American crew would do in combat conditions. Success or failure would be documented in exhaustive detail, photographed from multiple angles, and reported directly to senior Wehrmacht leadership, increasingly desperate for solutions to the Eastern Front's mechanical nightmare. What happened in the following hours would fundamentally challenge German assumptions about American industrial capability and engineering philosophy. The test would reveal a profound truth about radial aircraft engines adapted for military use, about automotive design principles mature beyond German industrial experience, and about the massive gap between theoretical engineering sophistication and practical battlefield reliability. Spring 1939, Connecticut. The Continental Motors Corporation in Detroit had already been building the R975 Whirlwind radial engine under license from Wright Aeronautical for nearly 10 years. Originally designed for civil aviation in the late 1920s, this 9-cylinder air-cooled radial had proven itself reliable in thousands of flight hours across varying climates and operating conditions. When the United States Army needed a power plant for its new medium tank development program, Continental's experience with the R975 made it the obvious choice. The engine's specifications reflected practical aviation engineering rather than theoretical optimization. 973 cubic inches of displacement, bore and stroke of 5 by 5 and 1/2 inches. Compression ratio of 5.7 to 1, conservative by contemporary standards but proven durable. The Continental R975 C1 variant produced 400 gross horsepower, the later C4 variant 460 horsepower. More importantly, both versions maintained consistent performance across temperature ranges that would disable more temperamental designs. The R975's ignition system represented decades of aircraft engine development. Twin magnetos provided redundant spark generation without any dependence on battery power. Each magneto was a self-contained electrical generating system that produced high-voltage ignition spark through magnetic induction as long as the engine turned. No battery failure could prevent spark generation. No cold weather degradation of battery chemistry could compromise ignition reliability. The magnetos simply worked, every revolution, regardless of ambient temperature. This design philosophy differed fundamentally from German tank engine practice. Maybach engines powering Panzer III, Panzer IV, Panther, and Tiger tanks all employed conventional battery-dependent ignition systems. Cold weather reduced battery capacity by 50% or more, making starting extremely difficult even with inertia hand cranks to supplement electric starters. German crews developed elaborate pre-warming procedures out of absolute necessity, not preference. Continental built the R975 using commercial automotive manufacturing techniques refined through mass production of civilian engines. Tolerances were generous compared to German precision engineering standards. Components were designed for ease of manufacture and replacement rather than theoretical optimization. American factory workers with basic mechanical training could assemble these engines reliably, while German production increasingly depended on skilled craftsmen becoming scarcer as the war continued. By the time the M4 Sherman entered production in early 1942, Continental had manufactured thousands of R975 engines. The company would eventually produce more than 53,000 Radial engines for armored vehicle use, far exceeding Wright Aeronautical's original production of the civilian version. This industrial scale, combined with decades of experience troubleshooting aircraft engine problems in diverse climates, had created a remarkably robust, design optimized for reliable operation rather than impressive specifications. Winter 1941 through 1942, Eastern Front. German tank crews experienced their first sustained combat operations in extreme cold, and the results were catastrophic. Army Group Center's advance on Moscow ground to a halt in early December as temperatures plummeted to -30°C and below. Tank engines that had functioned adequately in temperate European climates suddenly became nearly impossible to start. Morning procedures became elaborate rituals, consuming hours and enormous quantities of fuel. Crews drained coolant and oil each evening, storing the fluids in whatever heated space they could find. Warming the liquids required open fires or precious gasoline burned in improvised heaters. Pouring heated coolant and oil back into a frozen engine risked catastrophic thermal stress that could crack cylinder heads or seize bearings. Even successful warming often resulted in engines that barely turned over, burning excessive oil, and losing power. German tankers resorted to running engines for 30 minutes every 2 to 3 hours throughout the night to maintain operating temperature. This consumed staggering amounts of fuel, reducing already strained logistics capacity and leaving tanks immobilized by fuel exhaustion even when mechanically functional. In extreme cold, some units kept 1 or 2 tanks running continuously through the night to serve as battery charging stations and starting assistance for other vehicles at dawn. The psychological impact matched the mechanical problems. Crews lived with constant anxiety about whether their tanks would start when needed. Attack schedules hinged not on tactical considerations, but on how long it would take to get sufficient vehicles running. Defensive positions couldn't be repositioned because frozen tanks literally became fixed fortifications, tracks frozen to the ground, engines seized solid. The theoretical technical superiority of German tank designs meant nothing when the machines simply wouldn't function. Soviet T-34 tanks, powered by V-2 diesel engines equipped with compressed air starting systems and robust winterization equipment, consistently outperformed German vehicles in cold weather. German after-action reports documented this disparity with growing alarm. The Red Army could maintain operational mobility in conditions that immobilized entire panzer divisions. This mobility advantage translated directly into battlefield initiative, allowing Soviet forces to launch winter offensives when German units sat helpless, waiting for temperatures to moderate enough for their vehicles to start. By winter 1942 through 43, Wehrmacht leadership understood they faced a critical industrial problem. German tank engine design had prioritized power output and theoretical efficiency over cold weather reliability. Maybach engines produced impressive horsepower figures on paper, but those numbers meant nothing when the engines couldn't be started in combat conditions. The Army Weapons Office desperately needed data on enemy equipment to guide development of solutions, modifications, or entirely new engine designs incorporating cold weather capability. When War Daddy 2 arrived at Kummersdorf in spring 1943, initial testing focused on armor protection, automotive components, and transmission reliability. The captured Sherman impressed German engineers with its herringbone-cut transmission gears, superior cooling systems, and straightforward maintenance requirements, but comprehensive cold-weather engine testing would have to wait for winter conditions. Those conditions arrived in late November 1943, as temperatures dropped and the testing schedule expanded to include extreme cold evaluation. The Army Weapons Office issued specific protocols, multiple starting attempts under varying temperature conditions, documentation of preparation procedures required for successful starts, measurement of cranking speed, starting time, and initial running stability. Comparison with German tank engines tested under identical conditions using identical protocols. 5:45 hours, December 3, 1943. Test engineers approached the frost-covered Sherman in the pre-dawn darkness. Surface temperature readings showed the tank's hull at -19 degrees Celsius, slightly colder than ambient air due to radiative cooling overnight. The engine, sitting exposed to these conditions for 12 hours with no preparation whatsoever, would theoretically have reached thermal equilibrium with the surrounding environment. Engine oil would have thickened to consistency resembling heavy syrup. Any moisture in the fuel system should have frozen. The steel components would have contracted from thermal stress. Senior engineer Otto Hartmann led the test team, a 42-year-old veteran of Continental engine development programs before the war. Hartmann had worked directly with Maybach engineers on cold-weather starting solutions for German tanks, attempting modifications that improved performance, but never solved the fundamental problems. He understood engine design at a level that transcended simple testing protocols. What happened with the Sherman would either validate German design approaches or reveal that American engineers understood something fundamental that German industry had missed. Hartmann instructed his assistant to engage the electric starter motor. No pre-warming, no hand cranking to break loose seized components. Just direct engagement of the starting system as an American tank crew would do. The assistant climbed through the commander's hatch and positioned himself at the driver's station. Instrument illumination powered on. The main electrical system showed charge. He pressed the starter button. The Continental R975's electric starter motor drew power from the tank's 24-volt battery system. The motor engaged immediately, turning the engine crankshaft without hesitation despite the extreme cold and thickened oil creating substantial resistance. Cranking speed was noticeably slower than what would occur at normal temperatures, but the motor maintained consistent rotation. Hartmann counted the revolutions, timing everything with his stopwatch. 4 seconds, 6 seconds, 8 seconds. At 9 seconds of cranking, the R975 fired on one cylinder. 2. Then all 9 cylinders caught and the engine settled into a rough idle, sending clouds of white vapor from the exhaust as moisture burned off. The entire starting sequence, from button press to stable idle, consumed 11 seconds. No preparation, no preheating, no special procedures. The Sherman's engine had started in conditions that would have rendered most German tanks completely immobilized, and it had done so using only its standard on-board starting system. Hartmann stood frozen, watching the Sherman idle steadily as the morning temperature continued dropping. His engineering experience told him this should not be possible. The battery alone shouldn't have sufficient cranking power in these conditions. The oil viscosity should prevent adequate lubrication during initial rotation. The fuel shouldn't vaporize properly in the carburetor at this temperature. Yet all of those theoretical impediments had been overcome by a 10-year-old engine design adapted from civilian aviation use, an engine the Americans mass-produced by the thousands without any apparent difficulty. The test protocol called for extended idle periods to evaluate cold running stability. German engines that did start in extreme cold often ran roughly, misfired, or stalled within minutes as various systems failed to maintain proper function. The Sherman's R975 continued running with increasing smoothness as components reached operating temperature. After 10 minutes of idling, Hartmann ordered engine shutdown to repeat the test. 3 additional cold starts that morning followed the same pattern. Button press, 9 to 12 seconds of cranking, immediate firing and stable idle. The engine never required hand cranking assistance. The battery never needed supplemental charging. No preparation procedures were necessary. The Americans had somehow created a tank engine that simply worked in conditions where German designs consistently failed. This wasn't a small performance advantage or minor engineering refinement. This represented a fundamental philosophical difference in how engines were designed and built. Hartmann directed comprehensive documentation of the R975's cold weather starting capability. Engineers disassembled the magneto system to understand its construction and operation. They measured bearing clearances, examined piston ring design, analyzed the carburetor fuel delivery system, and tested every component that contributed to cold weather performance. The resulting technical report would run to more than 80 pages, documenting not just what the Sherman's engine could do, but attempting to explain how American engineers had achieved reliability German industry couldn't match. The magneto ignition system emerged as a critical design element. German engineers discovered that the magnetos generated adequate spark voltage through pure electromagnetic induction, requiring no battery power whatsoever. As long as the engine turned, spark generation was guaranteed. This eliminated an entire category of cold weather starting failures that plagued German tanks. Battery degradation, always severe in freezing temperatures, simply didn't matter for ignition purposes. The air-cooled radial configuration provided another significant advantage. German water-cooled engines required glycol-based coolant that became viscous in extreme cold and could freeze if not properly maintained. The coolant system itself added complexity and potential failure points. The R975 eliminated these problems entirely through air cooling. There was no coolant to freeze, no water jackets to crack from thermal stress, no coolant pump that could fail in cold conditions. The engine's generous bearing clearances, which German precision engineering standards would have rejected as sloppy manufacturing, proved ideal for cold weather operation. Thickened oil could still flow through the larger clearances, providing adequate lubrication during initial startup when German engines often experienced oil starvation and bearing damage. The Americans had accepted slightly lower peak performance at optimal temperatures in exchange for reliable operation across extreme temperature ranges. December 14, 1943. Reich Minister Albert Speer visited Kummersdorf for routine inspection of captured equipment testing programs. His agenda included observation of comparative trials between Sherman tanks and German designs under winter conditions. Speer arrived at 07:30 hours, accompanied by senior Wehrmacht officers and Armaments Ministry officials. Temperature that morning registered -22 degrees Celsius, colder than the previous test sessions. Engineers prepared multiple demonstrations. 3 Sherman tanks with R975 Radial engines would be compared directly against a Panzer IV with Maybach HL 120 engine, a Panther with Maybach HL 230 engine, and a Tiger with Maybach HL 210 engine. All vehicles had sat exposed overnight with no special preparation. The cold start comparison would be conducted simultaneously, providing direct evidence of relative capability. At Speer's signal, all tank commanders engaged their starting systems. The 3 Shermans fired within 12 seconds, their radial engines settling into steady idles despite the brutal cold. The Panzer IV required hand-cranking assistance after the electric starter failed to turn the engine over. The Panther's crew spent 18 minutes with hand cranks and auxiliary heaters before achieving a rough idle that immediately stalled. The Tiger refused to start at all despite 30 minutes of preparation attempts. Speer observed this demonstration in visible discomfort. As Minister of Armaments and War Production, he bore personal responsibility to Hitler for German industrial output and weapons performance. The Sherman's cold weather superiority couldn't be dismissed as minor or anecdotal. It was catastrophic evidence that American automotive engineering maturity exceeded German capability in fundamental ways. Every winter day that German tanks remained immobilized while enemy vehicles maintained mobility translated directly into tactical defeats, territorial losses, and ultimately strategic catastrophe. The demonstration continued with mobility trials. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Engineers wanted to evaluate not just starting capability, but sustained cold weather operation under load. The 3 Shermans moved through obstacle courses designed to replicate battlefield terrain, climbing steep grades, negotiating ditches, and traversing rough ground while their engines maintained consistent power delivery. Exhaust temperatures were monitored continuously. Oil pressure readings remained stable. Coolant temperatures, or rather the lack of coolant complications, meant one entire system of potential cold weather failures simply didn't exist. The Panzer IV, finally started after considerable effort, struggled through the same course. Its engine ran unevenly, power fluctuating as fuel delivery problems manifested in the extreme cold. The crew reported sluggish throttle response and hesitation during acceleration. After 20 minutes of operation, oil pressure dropped precipitously, indicating inadequate lubrication from cold-thickened oil that hadn't properly circulated through the engine. The test was terminated to prevent catastrophic bearing failure. The Panther, after 3 separate restart attempts following its earlier stall, managed to run long enough for limited mobility evaluation, but the engine temperature climbed dangerously high despite ambient air temperature remaining well below freezing. The cooling system, designed for temperate climate operation, couldn't properly regulate engine temperature when coolant viscosity increased dramatically in extreme cold. The thickened coolant flowed sluggishly through water jackets and radiators, creating hot spots in the cylinder heads, while other engine sections remained too cold for proper thermal expansion. The Tiger never participated in mobility trials. After more than an hour of preparation attempts, including external heating applied directly to the engine compartment, the Maybach HL-210 refused to maintain stable operation. It would fire briefly, run roughly for 30 seconds to a minute, then stall as various cold-induced failures cascaded through interconnected systems. Battery voltage dropped with each starting attempt as the cold sapped electrical capacity faster than the charging system could replenish it. Finally, Hartmann recommended abandoning further attempts to avoid damaging the engine through excessive cold starting stress. Speer's entourage witnessed 3 full hours of comparative testing that morning. The technical disparity couldn't be rationalized away or dismissed as testing anomalies. American tanks started reliably and operated effectively in conditions that reduced German tanks to frozen sculptures. The implications extended far beyond simple mechanical advantage. They revealed fundamental industrial inadequacy that couldn't be corrected through marginal improvements or component modifications. German tank engine design required complete philosophical reconception, something impossible to achieve while fighting a multi-front war with dwindling resources. What made the demonstration particularly devastating was understanding that the Sherman represented mass-produced American industrial output, not specialized equipment or prototype vehicles. The United States was producing thousands of tanks monthly, with this cold weather capability built in as standard equipment. American tank crews from California or Texas, men who'd never experienced truly cold winters, could deploy to northern Europe or theoretically to Arctic conditions and have their vehicles function reliably without any special training or equipment modifications. The R-975 simply worked, regardless of operator expertise or maintenance sophistication. German crews, by contrast, required extensive cold weather training and elaborate preparation procedures just to maintain marginal operational capability. Even then, cold weather reduced German tank effectiveness by 50% or more, not from enemy action but from mechanical unreliability. Offensive operations became nearly impossible to coordinate because nobody could predict how many vehicles would successfully start on any given morning. Defensive flexibility vanished when repositioning tanks required hours of preparation time. After the demonstrations concluded, Speer requested a private briefing from Hartmann about potential solutions. The 2 men stood in a freezing workshop while Hartmann explained the technical challenges with brutal honesty. Replicating the R975's magneto-ignition system would require retooling German electrical component manufacturing. Developing reliable air-cooled engines of equivalent power would demand years of development and testing. Redesigning bearing clearances and lubrication systems for cold weather operation meant abandoning current production tooling and retraining entire factory workforces. Every solution involved time and resources Germany no longer possessed. Speer asked whether captured Sherman engines could be installed in German tank hulls. Hartmann explained that the R975's radial configuration dictated specific hull design parameters. The engine's width and mounting requirements wouldn't fit German tank engine compartments without complete hull redesign. Even if mechanical integration were possible, parts supply and maintenance training would create impossible logistics problems. The Sherman's cold weather advantage came from integrated system design developed over years of commercial and military application, not from any single component that could be transplanted into German equipment. The conversation revealed what Speer had feared most. Germany faced industrial and engineering maturity gaps that couldn't be closed through wartime crash programs or captured technology exploitation. American automotive industry had spent decades solving practical problems of reliability, cold weather operation, and mass production quality control. That accumulated experience couldn't be replicated by German industry starting from behind while simultaneously fighting for survival against enemies with superior resources. The technical reports from Kummersdorf circulated through Wehrmacht headquarters and reached tank development offices at Maybach, Daimler-Benz, and other manufacturers. Engineers studied the R975's design features, attempting to adapt cold weather solutions for German production. But the fundamental problem wasn't individual components that could be copied. The problem was industrial manufacturing philosophy, decades of commercial automotive experience, and production capacity to implement solutions at scale. Continental Motors had spent 10 years refining the R975 through commercial aviation use before any military application. Problems had been identified and solved through thousands of engines operating in every climate and condition. Manufacturing processes had been optimized for mass production by workers with basic training rather than specialized craftsmen. Quality control systems had been developed through competition in civilian markets, where reliability meant commercial success or failure. All of this industrial maturity had been seamlessly transferred to military tank production. German industry lacked equivalent preparation time and commercial market pressure to develop such robust designs. Maybach engines were developed specifically for military use, tested primarily in controlled conditions, and refined through comparatively limited operational experience before being committed to mass production. Manufacturing required skilled labor becoming desperately scarce as the war consumed Germany's workforce. The entire industrial ecosystem that supported reliable cold weather engine design simply didn't exist in Germany with the same depth and breadth as in the United States. Post-test analysis by Hartmann's team concluded that replicating the Sherman's cold weather capability in German tank engines would require fundamental redesign of ignition systems, cooling systems, bearing clearances, and manufacturing processes. Implementation would take at least 2 years under peacetime conditions, probably longer given wartime resource constraints. Even if all technical problems were solved, German industrial capacity couldn't produce engines with Sherman-level reliability, while simultaneously maintaining current production of existing designs and developing new heavy tank programs. The cold weather testing revelation came too late and demonstrated too much. By December 1943, Germany had already committed to production of Panthers and Tigers with engines that would never match the Sherman's cold weather reliability. The industrial infrastructure to build radial aircraft engines at Continental's scale didn't exist. The decades of commercial aviation engine experience couldn't be replicated through crash development programs. The mature automotive manufacturing culture that made the R975 possible couldn't be created by government decree. German tank crews on the Eastern Front would spend the winter of 1943 through 44 and 1944 through 45 fighting the same losing battle with cold weather that had paralyzed them in previous winters. They would drain coolant and oil, heat fluids over open fires, hand crank engines for hours, and watch their tactical mobility evaporate while enemy tanks maintained operational capability. The mathematics remained brutally simple. A tank that couldn't start, couldn't fight, and a tank that couldn't fight might as well not exist. American tank crews receiving Sherman deliveries in winter conditions experienced none of these problems. The R-975 Radial engine started reliably at -20 degrees Celsius, -30 degrees Celsius, and in some documented cases even colder temperatures with minimal degradation in cranking time or initial running quality. Crews could button up for the night, wake at dawn, and have their tanks running within seconds of pressing the starter button. This operational advantage translated directly into combat effectiveness, allowing American armored units to maintain initiative and mobility in winter conditions that reduced German tank units to frozen defensive positions. The cold weather testing at Kummersdorf represented more than just comparative evaluation of enemy equipment. It was tangible proof that American industrial capability and automotive engineering maturity exceeded German theoretical sophistication in ways that fundamentally determined battlefield outcomes. Germany had pursued advanced tank designs with impressive specifications, powerful guns, and thick armor, believing technical superiority could overcome material and numerical disadvantages. The R-975 Radial engine demonstrated the fallacy of that belief. Technical sophistication meant nothing if the machine couldn't be reliably started and operated under actual combat conditions. The Americans hadn't built a better tank through superior weaponry or armor protection. They'd built a better tank through superior automotive engineering, manufacturing maturity, and decades of commercial market experience solving practical problems of reliability and durability. Hartmann's final report to the Army Weapons Office included a section titled Fundamental Design Philosophy Differences that attempted to explain why German industry couldn't replicate the Sherman's cold weather performance. The language was careful, avoiding direct criticism of German capabilities, but the conclusions were devastating. American engines were designed from the beginning to be manufactured by ordinary workers, serviced by minimally trained mechanics, and operated reliably by average soldiers under extreme conditions. German engines were designed to impressive specifications by highly educated engineers, manufactured by skilled craftsmen, and maintained by specialist technicians. In peacetime, or in short wars where industrial depth never became critical, the German approach produced excellent results. But in sustained total war against enemies with superior resources and mature manufacturing capabilities, the German approach was fundamentally inadequate. The United States could produce 50,000 R-975 engines because the design didn't require special skills or scarce materials to manufacture. Germany struggled to produce 5,000 Maybach engines that required constant expert maintenance and couldn't match the American design's cold weather reliability. Winter 1944 through 45. The final winter of the war arrived with German forces retreating on all fronts and armored units increasingly immobilized by mechanical failures, fuel shortages, and the same cold weather problems that had plagued them since 1941. Wehrmacht after-action reports from that winter documented instances of entire tank companies abandoning vehicles not destroyed by enemy action but simply incapable of starting in frigid conditions. By contrast, American and Soviet forces maintained high operational readiness throughout the winter. Soviet diesel engines, with their preheating systems and robust winterization, continued proving superior to German gasoline engines. American radial engines in Shermans, supplied through Lend-Lease to Soviet forces, functioned reliably alongside indigenous T-34 production. The Germans faced enemies on both fronts, whose tanks simply worked better in cold weather, enemies whose industrial capacity to produce and support reliable machinery exceeded anything German industry could match. The lessons learned at Kummersdorf about cold weather engine reliability influenced post-war German tank development in fundamental ways. When the Federal Republic of Germany began developing the Leopard 1 main battle tank in the 1950s, designers explicitly emphasized reliability and maintainability over theoretical performance specifications. They studied American automotive engineering principles and deliberately incorporated cold weather capability from the beginning of the design process, rather than attempting to retrofit solutions later. The Continental R975 Radial engine itself remained in service for decades after the war. France converted hundreds of M4A4 tanks with Chrysler multibank engines to R975 power plants in the 1950s, specifically choosing the Radial for its reliability and ease of maintenance. Many nations operating Shermans in post-war service prioritized versions with the Continental Radial precisely because of its reputation for reliable starting and consistent performance across temperature extremes. War Daddy 2. That single Sherman tank captured in Tunisia and tested exhaustively at Kummersdorf never returned to combat service. The vehicle remained at the proving ground throughout 1944, used for continuing evaluation programs and occasional demonstrations for senior officials. In spring 1945, as Soviet forces approached Berlin, someone made the decision to destroy test vehicles rather than allow their recapture. War Daddy 2 was likely burned or blown up during the chaotic final weeks, before Germany's surrender. But the legacy of that Sherman's cold weather engine tests survived in documentation, in the minds of engineers who witnessed them, and in the fundamental understanding they provided about American industrial superiority. Every frozen German tank that winter, every hour spent trying to start Maybach engines in brutal cold, every tactical defeat caused by mechanical immobility, all of it validated what the tests had proven in December 1943. The Americans had solved problems German engineers didn't realize needed solving, and they'd solved them through decades of commercial experience and industrial maturity that couldn't be replicated through wartime crash programs. The Continental R975 didn't win World War II through its cold weather starting capability alone, but it represented perfectly the industrial philosophy that did win the war: reliability over theoretical sophistication, practical functionality over impressive specifications, manufacturing maturity over engineering brilliance, decades of commercial competition and experience over military development in isolation. These principles, embodied in a 10-year-old aircraft engine design adapted for tank use, proved more decisive than any amount of technical innovation pursued without regard to practical operational requirements. 11 seconds. That's what it took for an American tank crew to have their Sherman running in conditions cold enough to immobilize entire German panzer divisions. 11 seconds from button press to stable idle, no preparation required, no expert maintenance needed, just straightforward, reliable function that worked every time regardless of temperature. That simple capability, multiplied across thousands of tanks and years of sustained operations, represented an insurmountable advantage that German industry never overcame. The mathematics were simple and brutally clear when examined objectively. A Sherman with a 400 horsepower Radial engine that started reliably in Arctic cold was infinitely more valuable than a Panther with a 700 horsepower Maybach that remained frozen and immobile at dawn. An armored division that could maintain 80% operational readiness through winter could execute missions that a division with 40% readiness simply could not attempt. Cold weather reliability wasn't just a convenience factor or secondary consideration. It was the foundation of operational effectiveness, determining whether armored units could fight at all during half the year in many theaters. The German tank that looked more sophisticated on paper but couldn't be started on a cold morning wasn't superior. It was inferior in the most fundamental way possible. The American tank, with a simple radial engine that crews could start with the press of a button, represented automotive engineering at its most effective. Not the most technologically advanced, not the most theoretically impressive, the most effective at accomplishing the basic mission of getting soldiers and weapons into combat reliably, day after day, regardless of conditions. That effectiveness was what defeated Germany. Not any single tank battle, not any specific technical advantage, but the relentless accumulation of industrial superiority expressed through countless small advantages like cold weather starting reliability. The Continental R975 was just one example among thousands of how American manufacturing maturity exceeded German capabilities in ways that fundamentally determined the war's outcome. Hartmann understood this by late 1943, watching that Sherman start effortlessly on frozen December mornings while German tanks sat immobilized. He wrote detailed reports documenting the disparity. He recommended comprehensive programs to develop equivalent German capabilities. He explained exactly why American engines worked better and what would be required to close the gap. But understanding a problem and solving it under wartime conditions proved fundamentally different challenges. German industry lacked the capacity to retool production around reliability principles, while simultaneously fighting a losing war on multiple fronts against enemies with superior resources. American industry had built reliability into its civilian automotive sector over decades of commercial competition, and simply extended those mature principles to military production with remarkable success. That experience gap was unbridgeable through crash programs or theoretical engineering excellence alone. So the Continental R975 Radial engine, that workhorse 450 horsepower design derived from 10-year-old aviation technology, continued starting reliably in conditions that paralyzed German tanks. It did so not because American engineers were more brilliant than their German counterparts, but because American industry was more mature, American manufacturing culture was more developed, and American commercial market experience had solved practical problems over decades rather than months. Those advantages, multiplied across entire industrial economies and translated into thousands of reliable machines, decided the war as certainly as any general's strategy or soldier's courage. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now and don't forget to subscribe.